equals 6, it gives us the graph of a function. It says the graph of f of x is given. In part A, it says if x equals -4, what is f of x? What is the point on that graph? So we're going to read our value right from the graph. So x equals -4. What is negative for f of x? So let's go find -4. So here, -1, -2, -3. Right here, -4. So as we meet up with our graph, right here is our point. So I'll go ahead and write that point in here. So we have -4. So it looks like the output, is right here at 1, 2, 3, 4. So -4, 4. So again, if I'm looking at x equals -4, so what's f of x? Right, f of -4 would equal 4. So the value would be 4 on that, right, on that function. Now let's turn around and go the other way. Now they give us the output. So the output -10. Let's find -10 on here. We'll put it here in a different color. We'll do it in red. All right. And as we do that, let's go find that. So again, this is our y value. So y equal -10. So looking at -10, right here is -10 on the y-axis. Well, as we meet up with our graph, right here is our ordered pair, which looks like what? Let's go ahead and write that ordered pair down. So this is 1, 2, 3, 4. Well, right here is 3. So 1, 2, 3. So at x equals 3, right, we got this point, 3, -10. So there it is. So that implies x would equal -3, right? And read it right off the graph, right, with that function. So they gave us the graph, right? I don't know why I put -3. Somebody correct me, that is a +3. We're on the positive side of the x-axis. So x equal to 3, not -3, right? But again, we've solved it, right? So we solved the function. We found out when the function -10, the input of 3 gives us output -10. We see that ordered pair of 3, -10 on our graph. So reading graphs is something we can easily do. It's nice if they give us the graph. We can easily read the value or read the solution, right, based off the graph there. We've got all our points in front of us. All our ordered pairs x and y. So we'll know x and y right from the graph. Looking at problem 7, wants us to find the domain of the following functions using a interval notation. Well, you look at example, they got a linear function. No undefined values, right? You're not dividing by x. You don't have any even root terms, right? So we're talking about domain quickly, all real numbers. So it said use as a interval notation. So of course, all real numbers be -infinity to infinity. So it covers the entire x-axis, a line. Line's continuous, no breaks, covers the entire x-axis. Now, as you look at our next example, well, we have a rational function. Well, our denominator, right, with a rational function cannot be 0. So that stands out to me. So let's go ahead and take that denominator, x squared plus 5x plus 6. And let's see what happens. What are those zeros in the denominator? We'll exclude those. So find the restrictions. Find the undefined values. Now, with this quadratic, of course, every quadratic has 2 linear factors, and they've given us one to easily factor. We need the x squared, so we'll need x and x up front. And what factors of 6, right, going to work together to make this middle term, which is 5x, happen? Well, 2 times 3 is 6, and 2 and 3 do add up to 5. So we would need a +2 and a +3. So if you distribute or fold that out, right, our outer product's 3x, inner product is 2x. So again, I wanted to go ahead and factor, and I've done that. So again, 3x plus 2x add up to 5x. And as we apply the zero factor property, we know that x plus 2 can equal 0, or x plus 3 can equal 0. Now again, we know these are zeros of the denominator, so they can't be 0 to satisfy our function, so we'll make note of that. So for solving this down. And then our last step, let's go ahead and move those over. Let's subtract those over. Use our addition property of equality. We'll subtract the 3 or add a negative 3 to both sides. So we have x being not equal to negative 2, and also x cannot equal negative 3. So if we had negative 2, right, or we had negative 3, we would have a problem. Our denominator would become 0. So these are our undefined values, right? I'll make that note here beneath it. All right, so that implies, as we look at our domain, let's write our domain, all these x values at work. So remember, as we're looking, you can draw it on an x line if you like. Here's all real numbers, x. So negative 3, for example, and negative 2. Right, we'd have a break on our graph at these two locations if you were to graph it. So our domain, as an interval goes, right, would be all x values less than negative 3, right, or all values greater than negative 3 and less than negative 2, or all values greater than negative 2. So there's our domain, right, as a interval, which is our preferred form. So there's a list of every real number except negative 3 or negative 2. So again, that leads you to your domain there. All right, let's move on to the next one. Now, I like the next one. Example C, we got a couple of things going on in this one. First thing I want to make note of is this x squared minus 4. It's down here in the denominator. We know that x squared minus 4 cannot equal 0. All right. I want you to look at the numerator also. In the numerator, I've got an even root. I've got a square root. A square root, right, can't be negative. So we have to set it greater than or equal to 0. So we've talked about that in our previous example. We worked with the even root function. So there's two things going on with this one. Even root in the numerator and a denominator with x. So we got to look for those real number zeros in the denominator, exclude them. So let's go ahead and work these two. Now x squared minus 4, I'm going to go ahead and factor that. The difference of squares. X squared minus 2 squared. So that's x minus 2 times x plus 2. So we apply our zero factor property. X minus 2 cannot equal 0, or x plus 2 cannot equal 0. So that implies x cannot equal 2, or x cannot equal negative 2, right, as we solve for x. So we subtract those numbers or add them over to the other side. Let me show it work there. Well, there's two domain restrictions. So these are undefined values. So keep that in mind, right, when we talk about our domain. And we also have x plus 5 greater than or equal 0. All right, well, let's go ahead and simplify that further. Well, if it's got to be greater than or equal to 0, as we solve for x, right, we would go ahead and subtract 5 on both sides. And that implies x got to be greater than or equal to negative 5. So here's our domain restrictions. So with that, let's draw in an x line. So here's our x-axis. If we were to graph this function, here's all real numbers x. Let's place what we found on here. So negative 5, critical value. We said we had to be greater than or equal to negative 5. We also found that negative 2, right, is a undefined value, and positive 2 is undefined value. So I'm going to put a little open circle. We can't include these. Why? Because our denominator becomes 0 at both of these locations. So as we look at our domain, we can be equal to negative 5 or greater than. So you can see what happens with our graph. I'll shade it in. There's all the values. I shade in, right? All values greater than or equal to negative 5. We got to exclude negative 2 and 2. So our domain, now we can easily write it. So I like to draw in the x line to make it a little easier to see. And let's go list these intervals, right? We just found our intervals. So we got greater than or equal to negative 5. So bracket, need a bracket on it. I want to include it because it's got to be equal to negative 5 or greater than. And negative 2, we need to exclude. We need a parentheses. So greater than or equal to negative 5, less than negative 2. Those numbers work. We can plug in x, get an output. We can also look at the numbers that are greater than -2 and less than 2. So need parentheses on both. Numbers like -1 and 1 and 1.9 and -1.5. Those are all domain values. They're okay. Just -2 and 2 are not. Or all the x values greater than 2. So there's our domain for this given function. A couple different restrictions. And this ties into our last example in this set. We also have a rational function in this next one, but our denominator is an even root. So with that, since it's in the denominator, we know even roots must be negative or must be positive, right? Or 0, because it can't be negative numbers. So usually we set it greater than or equal to 0. Well, since this is in the denominator, all we got to do is set it greater than 0. So that'll exclude the 0 from the denominator. So greater than 0, right, if it's in the denominator, right? Even root, and I'll make that not even root in denominator, right? Can't be negative, right? Or 0, because we can't divide by 0. So we had to exclude 0 in this one. Now, as we solve that, of course, it takes one step. So we add the 8 over. We're getting ready to see our answer. We're getting ready to see our domain restrictions. X must be greater than 8. So here's our domain. All real numbers greater than 8. So parentheses 8 all the way to infinity. So 8 to infinity. There's our domain. There's all the x values. So you graph it. That's where it'll take place on the x-axis. So I hope that helps you with the domain. Those are good review problems. Back to when we were talking about functions.